So about the speaker, Nejat Said from Technical University of Graz. He has received his bachelor and master degrees in electrical engineering from Shahid Beheshti University and Amikabia University of Technology in Tehran, Iran in 2015 and 2018 respectively. He is currently working towards a PhD degree in electrical engineering at Electric Drive Machine Institute at the Graz University of Technology in Austria. He is also with Christian Doppler Laboratory of Brushless Drive for pump and fan application, and his research interest includes the noise and vibration of electrical machine and fractional horsepower electric drives. So, Ms. Nejat Said, I will give you the ball now, and I'm curious about your presentation.
Yeah, thank you very much. Okay, let me share my screen. Okay, I hope you can see the correct screen.
Yes.
Okay, great. Hello, everybody, and welcome to my presentation. My name is Nejat Said, and the title of my presentation is Effect of the Interaction of Different Manufacturing Imperfections and the Unbalanced Radial Forces in a Sub-fractional Horsepower Single-Phase BLDC Motor. I would like to start with a short introduction about these small machines, and I will briefly talk about manufacturing imperfections and their effect on noise and vibration. Afterward, I will present my simulation results with JMAG, including single effect analysis of manufacturing imperfections and also their combination. And in the next step, I will show you some experimental results, and I will end with a conclusion. Okay, let's start with an introduction. Okay, when it comes to cars, there are two trends. Cars are becoming more and more quiet, no doubt, and the number of auxiliary drives is increasing in modern electric vehicles in too many applications. For example, in a mid-size modern electric car, there is more than 100 small electric drives, mostly in safety and comfort applications. And given these two trends, we can say that the noise of auxiliary drives is no longer masked by the noise of internal combustion engine, and they can be disturbing, especially in such applications that are close to the passenger. As a result, we can say that knowledge of noise sources in these auxiliary drives is important, as they can induce airborne and also structure-borne noise. In this presentation, we are talking about mass-produced sub-fractional horsepower BLDC machines in the range of 1 watt. And the application that we are focusing on is an automotive cooling fan, which can, for example, be used in LED headlight. And you can see this small fan here in left-hand side. In mass production of these auxiliary drives, minimum cost is often still the primary design criteria, as long as their functionality is not compromised. And that means that they are often single phase instead of three-phase motors, leading to fluctuating power and torque. And typically they have high carrying torque on torque ripple due to the same number of slots and poles, and it can be the source of noise, and also due to their production, low cost production, they have a rather large manufacturing imperfections, which can be another source of noise. as I mentioned, most of these drives are single phase machine, and in this fan structure we have outer rotor BLDC motor, and in most cases they are salient pole motors, like illustrated here, and in some cases they are claw pole motor, as shown here in right hand side. The example case that we do simulation, and it is a 4-pole 4-slat autorotor BLDC salient pole machine. Okay, so the target is to investigate the unbalanced radial forces and under the situation in which there are several manufacturing imperfections, to see their interaction and their effect on noise and vibration eventually. Okay, let's start with brief introduction about manufacturing imperfections. Literature shows that these 3 manufacturing imperfections have a significant effect on unbalanced magnetic forces, including dynamic and static eccentricities and non-uniform magnetization. As you know, eccentricities have their origin in the misaligned centers of the rotor and stator, and they differ in the center of rotation. Actually, in this case, in the case of static eccentricity, the rotor rotates around its own center, and in dynamic eccentricity, it rotates around stator centers. So eccentricities make an uneven air gap. It means in some parts the air gap is smaller, and so in some other parts it's larger. Here in these 2 short videos, I want to show you how they behave. The smaller air gap is marked here by this red marker. For example, in this case, in the dynamic eccentricity, when a rotor rotates, the smaller air gap is rotating as well with the rotor rotation. But in static eccentricity case, it's stable at the specific position, which is the initial angle of eccentricity. This difference make their unbalanced radial force different, which I will talk about them in next few slides. And non-uniform magnetization, which is rather common in low-cost applications, is defined here as a difference between residual flux density of different poles, which is shown here in this right-hand side figure. Okay, here you can see how we can implement eccentricity and non-uniform magnetization in JMAG. It's quite easy. In rotation setting, you can easily implement any kind of eccentricity that you want. And for non-uniform magnetization, we can define different residual flux density in magnet properties, and we can define any of poles and define a different residual flux density for them. Okay, let's go to simulation result. This slide shows unbalanced radial forces generated by static eccentricity and dynamic eccentricity. Besides the relative eccentricity, which is shown by delta, another parameter which is important to be considered is the initial angle of these eccentricities, which is shown by beta in these 2 diagrams. The resultant unbalanced magnetic force in X and Y direction and the amplitude and phase of radial one are illustrated in these figures. You can see also the resultant force in Cartesian coordination look different, but the radial one are quite similar in terms of waveform shape and also amplitude. But the big difference between these 2 cases is the phase of the unbalanced radial force. In static eccentricity case, it's stable, and it shows us that the resultant force vector doesn't rotate. But in dynamic eccentricity, it's rotating, and it's easily distinguishable with the phase of radial force vector. And here, similar to eccentricities, we can define an angle for non-uniform magnetization, which is defined as the angle of the middle of pole pair with the higher residual density, flux density, which is shown here by this dashed line in the left-hand side. And in this case as well, you can see the X and Y forces, which are similar to dynamic eccentricity because their main harmonic is first harmonic, and there is phase difference between X and Y forces. But again, the radial force is similar to dynamic eccentricity and static eccentricity. And in this case as well, the resultant force vector is rotating like dynamic eccentricity. It shows us that non-uniform magnetization and dynamic eccentricity have a quite similar behavior, and it was the main motivation to investigate their combination to see what happened if we have these two at the same time. Here now we can go ahead and compare the harmonic content of the resultant radial magnetic force of these manufacturing imperfections. As shown in this figure, all of these three have similar harmonic content, which is multiples of force harmonic, including zeros, fours, eights, and so on. And the difference between their amplitude is related to the difference of the relative eccentricity on non-uniform magnetization. So to see the difference between the harmonic content of these unbalanced magnetic forces, a two-dimensional fast Fourier transform can be implemented on radial magnetic force density, which includes several traveling waves, and each traveling wave has a time harmonic order n, which you can see in the equation, and spatial one, which is r in the equation. Okay, and this contour shows us the radial force density in ideal single phase machine without any manufacturing imperfection. The circumferentials order, as you can see here, represent the number of maxima of the wave, and their sign indicates the direction of rotation of each wave. And zeros harmonic represent the pulsating force. As you can see here, in ideal case, only time and spatial harmonics with force multiples appear in the spectrum, and we can compare them with situations that we have manufacturing imperfections in. Next slide. Here you can see the spectra in a case that we have static eccentricity. As you can see, we will have two other circumferential order, which represent the unbalanced magnetic forces, negative one and positive one. As it's easily distinguishable, we won't have extra time harmonics. We just have some extra spatial harmonics. But in the case of dynamic eccentricity and non-uniform magnetization, you can see that we will have both time and spatial harmonics, extra time and spatial harmonics, and their spectra is quite similar. Okay, we can now go to the combination of manufacturing imperfections. Before starting their combination, it's important to have a simple model of them to know in which situation dynamic eccentricity and non-uniform magnetization can cancel themselves out, and how much of relative eccentricity and relative non-uniform magnetization do we need. In this simple model, these forces can be presented by subtracting the maximum and minimum forces which happen at the minimum and maximum area gap lenses. If we do some simple mass, neglecting saturation and MMF drop in iron parts, we can have an equation for the maximum force for dynamic eccentricity as it's shown here, and a similar one for non-uniform magnetization as well. And if we make them equal, it will lead to this equation, which shows us the relationship between non-uniform magnetization and dynamic eccentricity. And if we plot it here in this figure, you can see, for example, for 10% of non-uniform magnetization, we will need 12% of dynamic eccentricity to cancel out the force of non-uniform magnetization. And here in this slide, we can investigate their combination. We have three cases here. In case one, we just have non-uniform magnetization. And in case two, which is best condition, the dynamic eccentricity and its phase located exactly in opposite direction of non-uniform magnetization, and a gamma, which is the phase difference between these two vectors, is 180 degree. And in worst case, we will have both vectors exactly in the same direction, and we got these numbers from previous slide. If we see the resultant radial force, you can see in case one, we have some unbalanced force. And in case two, which is best condition, dynamic eccentricity could cancel out the force of non-uniform magnetization. But in case three, which is the worst condition, dynamic eccentricity magnifies the unbalanced radial force from non-uniform magnetization. It shows us the huge variation from 0 to 0.5 Newton depends on the phase difference between these two manufacturing imperfections. Yeah, the resultant unbalanced force highly depends on phase difference between these two manufacturing imperfections. So if we add some static eccentricity as well to this combination, 20% relative static eccentricity, you will see that in all cases, static eccentricity shows itself regardless of gamma, but it depends on gamma, the amplitude of radial force change, because we have dynamic eccentricity and non-uniform magnetization. And it still shows us the high dependency on gamma. If we see the result from two-dimensional fast Fourier transform as well, you can see in these three cases from different values of gamma, in this case 180, 90, and 0. This case was the best case, and the wave which represent the unbalanced magnetic force, the dominant one, is circumferential order -1 and first time harmonic, which is located here. The amplitude of this wave is 46 decibel, and when we decrease the gamma, it increases. For example, for gamma equals to 90 degree, we have 69, and in worst case, it could be 72. Here again, we could see the high variation of unbalanced radial force from 46 to 72, which is a real huge variation of unbalanced magnetic force. Okay, let's go to experimental results. Here you can see the experimental result of force measurement of the aforementioned fan equipped by salient pole single phase machine. And the results of 23 low-cost fans from same production line are investigated in this experiment, and you can see the results. And again, we can see the significant variation of the amplitude of force first harmonic from almost -20 decibel to 45, which is a very huge variation of this first harmonic. And now we can say that these combinations can lead to uncertain structure-borne noise behavior of these small drives. And let's come to an end with a conclusion. We say that manufacturing imperfections are rather large in mass-produced low-cost small drives, which can lead to noise and vibration. And the effect of combination of manufacturing imperfections and the formation of radial magnetic forces have been studied using finite element analysis. And it has been shown that both dynamic eccentricity and non-uniform magnetization can cancel themselves out in some cases, and the amplitude of resultant unbalanced radial force highly depends on their phase difference. And this parameter increases the uncertainty of NVH behavior of sub-fractional horsepower BLDC drives. Thank you very much for your attention.
Yes, thank you very much for this presentation. And I think there will be some questions from the participants. Please ask your question via the Q&A session in Zoom or the chat functionality in Zoom. This would be the most suitable.
I have a question regarding slide 17.
Okay, let me share the slides again. Slide 17 here.
Exactly.
Yeah.
How did you come up with the value, the static eccentricity value of 20%?
Actually, it's a random value. We just want to see the effect of static eccentricity and the combination of dynamic eccentricity and non-uniform magnetization. Because it doesn't matter if you choose any value for static eccentricity, you will see the effect of it and the resultant radial force.
Okay. Okay, thank you.
You're welcome.
Okay, perhaps other questions from the audience via the chat or the FNQ functionality in Zoom. Yes, there is one question here in the chat. Could you name other imperfections that can also contribute to unbalanced forces?
Yeah, sure. Actually, there are a lot of manufacturing imperfections, maybe due to, for example, the bearing. We have several unbalanced radial force related to bearing unbalancy, some other eccentricities in axial direction, for example, which leads to unbalanced axial force, because we had investigated the unbalanced radial force in this case, but unbalanced axial force can be disturbing as well. But we just investigated 3 of them as an example of some other manufacturing imperfections, because they can represent them as 2 different kind of manufacturing imperfections.
Yes. Thank you. Well,
maybe another question from my side. How can you control or what design aspects should you take to improve the dynamic eccentricity?
Actually, most of these manufacturing imperfections have uncertainty, and almost it's not possible to control them. But we can have some design criteria to design these machines to be less sensitive to manufacturing imperfections. But their origin is not controllable.
Okay.
Yes, there's another question from the same participant from the audience. What do you think about the effect of magnet positioning and geometrical tolerances in this kind of study?
If I got the question correctly, let me.
I could repeat it. What do you think about the effect of magnet positioning and geometrical tolerances in this kind of study?
Yes, if we define magnet positioning like that, because it highly depends on, in this case we have a magnet ring, it highly depends on the initial position of the magnet and the center of stator and rotor. And it was the main parameter that we have investigated here as a gamma, which is the phase or angle difference between this non-uniform magnetization and the eccentric center of rotor and stator. I hope I could answer the question.
Yes, was this the answer to your question? Looks like, but perhaps if you have, so if the audience want to know more, it's also a possibility to send us messages afterwards, and then we can also answer this question later.
Yeah.
There's another question. What were the main bibliographic references you used? Could it make it available in the future?
The reference of this research, they mean, I guess. Actually, it will be published soon in ECC conference. That maybe it will be available very soon, maybe in 2 months.
In 2 months, okay.
Yeah.
And the main bibliographic references, could you give more information about it?
Actually, I didn't get it. What main reference of this research they mean?
Yes, that's what I understand. That's what I understand.
Actually, there are several research that they have investigated the combination of manufacturing imperfections, but the new point of this research is considering phase difference between these manufacturing imperfections, because in the past they just considered them in worst condition, which there is no phase difference between them.
Okay, thank you. So we had some interesting questions. I'm not. Perhaps we wait just a minute. Perhaps there will be other people who have questions, but just yes, there is another one. This time again in the chat. I meant for example, the four magnets or four teeth can have different dimensions. Then it means some asymmetry and consequently some unbalanced force. Could you comment the importance of these imperfections compared to eccentricity?
Yeah, it's a good question. This asymmetricity from magnets is the same with non-uniform magnetization, but for the iron parts, it's true, and they are important as well. But their model will be the same exactly with eccentricities, because we will have some non-uniform air gap again and some unbalanced forces. They will be important as well, and we can maybe use this model to investigate their effect on unbalanced radial force. But yes, they are important.
It seems it is somewhere another question. Let me see. No, but yes, it would be so. If there are any more questions, please put it in Zoom. Be helpful. We'll just wait 1 minute and to see if there will be more questions. Okay. Okay. So it seems there are no further questions, but there was a couple of interesting questions. Nijat said, thank you very much for
thank you.
presentation, for having answered the different kind of questions, and to the audience a message. So if you have further questions, then you can send them to us. We will be happy to answer them after this presentation. And from my side, I have two information to share. Firstly, yes, I hope you can see my screen. Normally you should. Do you? Ahmed, you can see my screen?
Sorry, I was muted. Yes, I can see your screen.
Yes, just the information about for the people who are not so, for them, not used to use the GMAC. So we propose again GMAC trainings for beginners in November at the Leibniz University in Hanover. It will be an on-site and online event, 4 sessions from 4 to 25th of November. And at Heilbronn University, there will also a GMAC training, a get started training on site at the end of November on 23 and 24 of November. And you can just register on powersysolution.com. And of course, if you need more information or have wishes to have customized trainings or individual coaching sessions with GMAC or studies, then just contact me, me and the other people from PowerSys. We'll be happy to work out customized offer for you. Yes, and then the last slide is just to inform you about the next presentation. So now there is a small, let's say, a small break, about 1.5 hours approximately, and then we will stay in Graz. We just switch the place in Graz, and it's Mohamed Essam Ahmed from AVL in Graz, who will present advanced electric drive modeling with temperature and NVH adaptive control. For this presentation, he will use the PSIM and GMAC software suite. This presentation will start at 2:15 Paris time. So I would be happy if you could also join this presentation. So thank you again for your attention, Nejat. Thank you again for your presentation, for having answered the questions, and I wish you interesting GMAC and PSIM user conference. And I wish you a nice day.
Thank you.
Bye.
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 Okay. Dun.